Good afternoon. It's good to see all of you who were able to figure out where it was located. My name is Qui Bulow, college class of 1980, medical school class of 1984, and parent of 2 current students. I just shipped them off this morning because quarter is starting tomorrow. As president of the Alumni Club of San Diego, I would like to thank you all for coming to this afternoon's Harper lecture. You'll have a chance to hear some exciting cutting-edge science and also to connect and socialize with your fellow alumni. I would like to take a few moments to thank the members of the Alumni Board of Governors, the volunteers of the Alumni Schools Committee. I know some of you volunteer for that organization, and the board members of the San Diego Club. I would also like to give a special shout out to Robert Fung, the immediate past president, who just concluded his 8 years of dedicated service. And we also have Jen Leonard Benson in the back at the registration desk. She is the Associate Director of Regional Programs, covering everything from Arizona up to Vancouver. Their leadership and your support make wonderful events like this possible. So please join me in giving a round of applause for their service. Now, please welcome Tracy Publishin, Executive Director of Campaign Management for the University of Chicago.
Thank you, Qui. I'm delighted to be here with you all, especially in this beautiful weather that you have every day here in San Diego. As Qui mentioned, I'm the Executive Director of Campaign Management for the University of Chicago. I'm also a proud Chicago Booth graduate from the class of 2006. Today is our second event in this fall series of Harper Lectures. We are going to 16 cities this fall. We started in Chapel Hill a few weeks ago, and we'll be concluding in Mumbai in November. I hope you're enjoying the chance to connect or even reconnect with the University of Chicago and with one another this afternoon. I'm here to talk about the campaign, but before I do that, I thought I'd take a moment, and as Qui mentioned, this past week was O Week on campus, and for those of you that may be able to remember your first week on campus, we welcomed 1,500 students across 12 units and programs with a welcome convocation. And I want to share with you some of President Zimmer's remarks from the welcome convocation last week. Here's what he said. "You will not find at Chicago an environment of easy and comfortable belief in the latest politically correct view of the world. What you will discover is a community that finds intense and rigorous engagement tremendously exciting, enjoyable, challenging, empowering, and gratifying. What the analytic culture of inquiry at Chicago provides is a lifelong set of skills and approach to the world that eschews simplicity and comfort in favor of analysis, inquiry, and recognition of complexity." This is pretty amazing, right? And I know you'll find some of these values here today with our lecture. Our university was founded on the basis of philanthropy. In fact, this fall, we're celebrating 125 years, and the campaign honors this tradition and milestone by challenging us to engage 125,000 alumni by 2019. Of course, we also aim to raise $4.5 billion. So how are we doing? To date, we've raised more than $2.5 billion, and we've engaged nearly 56,000 alumni with the university. Those alumni have made a donation, they've volunteered, they've participated in events, and they've engaged with us on social media. I mentioned that I'm a Booth alum, so that means I love data, and I want to share some stats with you. 125,000 alumni represents 80% of our alumni community. 80%. This is quite an ambitious goal. California is home to nearly 9% of our alumni population, 15,600 alumni. Here in San Diego, we have 1,225 alumni. A third are graduates from the college, a third are graduates from Chicago Booth, and 11% from the Social Sciences Division. And 46% have graduated since 1990. So far, in San Diego and the state of California, we've engaged 35% of the alumni in these markets, with 2/3 coming from donations. It's important for alumni to engage with the university on multiple dimensions to help strengthen and extend our powerful network that fosters personal satisfaction and professional success. Your attendance today is a step in that direction. Thank you. So today, I'm asking you, if you haven't already, to consider investing financially, serving as a mentor, hiring a fellow alum, volunteering with the Alumni Club, and connecting with the university through social media. And as President Zimmer says, we are asking you to do still more so that the University of Chicago in the coming decades will succeed far beyond reasonable expectations. So thank you for coming this afternoon. I hope you'll enjoy the event.
The University of Chicago is urban,
global, courageous,
unusual,
phenomenal,
rigorous,
fabulous,
outspoken,
economics and pizza,
pushing borders,
invigorating,
an intellectual crucible
that pushes you to be your best every day.
From its inception, the University of Chicago focused on rigorous, intense inquiry. It's defined everything about what the University of Chicago is today and what it will be in the future.
The core curriculum is the symbol of who we are. Our mission is to get very talented students and to put them through a program of systematic, interdisciplinary training, and 4 years later graduate Chicago intellectuals.
I'll bring up a discovery that we've made, then I'll proceed to criticize my own discovery. It's through self-criticism you create a learning culture of critical inquiry.
We aren't just talking at each other, we're listening. And at the end of the class, I may have a completely different perspective on the issue.
Some excellent students over the years. They were very much my teachers. It changed my work. It just exposed me to a world of ideas.
I was the beneficiary of a scholarship from the University of Chicago. I could not have gone to business school without that scholarship.
I just feel so grateful that I was selected to kind of be among the minds and the intelligence and the incredible people. It's been the best experience of my life.
I think supporting young people to pursue their dreams opens up the world to you. All we ask of anybody is that they do the same to the next generation.
The university is really made by the people in it.
really very competitive.
Very unruly.
Seeing all the crazy, amazing things that they're doing.
Curing diabetes, cancer.
Innovation, more entrepreneurship, new ventures, new technologies.
Really forces me to push for something beyond what I'm doing.
In higher education today, the humanities are really in retreat. We really think that it's a responsibility to continue to foster growth of the humanities. The Collegium will allow teams of humanists from all over the world to tackle problems that society needs to deal with.
The Institute of Molecular Engineering is organized around solving water, energy, health problems through designing matter from molecules up. Just solving one of all of these problems that we're working on would be tremendous.
You're part of an intellectual community
that attracts individuals who are intellectually fearless.
That will bring together experts from different disciplines to help solve problems. We're exploring opportunities to create more portals for the community and people in the city to come into the university and both get some of the knowledge that we have, but also share their knowledge with us.
Lots of people are skeptical about the ability to use social programs to prevent crime. What we've tried to do is to generate evidence that is so rigorous and so compelling that the most skeptical skeptic will have to acknowledge that there's really something here. 1 year of participation in the Youth Guidance and Becoming a Man program reduced violent crime arrests to these kids by over 40%, which I think really challenges the conventional wisdom that the only way that you can control crime and violence in the United States is through locking up millions and millions of people.
And if you show the impact, it has global reach. Billions of people, not just millions, billions of people that you can get to.
It's very important in a world which is becoming more integrated that you have these global universities.
We now have a rather more ambitious global strategy with the same gold standard quality of curriculum and teaching.
Students are going to want experience of understanding other cultures because this is going to be the world that they are functioning in over the coming decades.
Can we bring people, scholars, politicians, administrators from these different areas also together to discuss what's going on?
To debate the big challenges facing the world.
Human illness limits society. And accordingly, fixing that, addressing it, is hugely important. It's transformative.
I had been diagnosed with metastatic or advanced breast cancer. The first thing Dr. Fumi Olopati said to me is, I want to find out more about your tumor so that I can personalize the treatment for both you and the tumor. The survival rate for metastatic diseases was 1 to 2 years. I really must say that I have survived the odds. I mean, I'm still sitting here, standing here 10 years plus.
You know what? It's worth every day getting up and supporting patients like her.
We have an enormous obligation to the people who gave us the opportunity today to do what we do with these young people, and in turn, they have an obligation to support those who come after us.
The question for us today is, how do we realize these values in a powerful way going forward?
Together, we are spreading grace and humanity.
Together we are thinking about ways in which you could have an impact on society.
Together,
We have the potential to change the way people think about urban problems.
Together,
We make amazing discoveries possible.
It's part of our DNA. It's who we are.
It's a big, big universe here.
ours is the university of great discoveries.
Ours is the university of fearless inquiry.
Ours is the university that develops ideas that change the world.
Hello, my name is Brian Clay, and I graduated from the Biological Sciences Division in 2008. For more than 125 years, the university has attracted and supported a faculty of transformational thought and impact. Today's Harper Lecture continues a tradition of bringing faculty and alumni together to celebrate and explore world-changing ideas. I'm honored to be introducing our Harper Lecture speaker today, Giulia Galli. When I look back at some of the reasons why I thought the University of Chicago was a great place to perform my graduate studies, the main reasons are, one, they have a great faculty who are often leaders in their fields, and also you have access to cutting-edge technology on campus that allows you to perform exciting and new research early in your career as a young researcher. And Dr. Galli's lab is a prime example of that. She's a leader in the development and use of theoretical and computational tools to understand and predict the properties and behavior of materials, and she's been a leader in her field for that research. Giulia Galli is a Liew Family Professor in Molecular Engineering, Senior Scientist at Argonne National Laboratory, and Senior Fellow of the Computational Institute. She's also a Fellow of the American Physical Society and the American Association for the Advancement of Science. She has received numerous awards from the Department of Energy and the Lawrence Livermore National Laboratory. Please welcome her with a round of applause as she comes and gives her a talk. Thank you.
Thank you very much for your kind introduction, and it's a real honor for me to be here, and thank you for being here this afternoon, and it's a real pleasure to be in San Diego, and speaking of kids, like the president said, my younger son goes to school at UCSD, so it's even, an additional pleasure to be here today. So I'll get to see my son, who has started actually 2 days ago. So I'm here to tell you about our computational research in water. So here, what do I mean, just to get started, when I talk about an integrated microscope for water? Everybody knows what a microscope is. Here, we will be talking about an unusual microscope, a microscope made from data collected by doing computer simulation and then connected to real experiment to understand the structure of water. So everybody knows water, right? I work on many different kinds of material science issue, and there are materials or substances that I have a very hard time relating to people, but water, everybody knows water, and everybody knows salt water. And so why are we studying water? Actually, water is a very well-known substance. Everybody knows it. And everybody, like me many years ago, is probably convinced that we know water. We know it very well, but it's very mysterious. And especially if you look at the structure of water at the molecular scale. Here is the molecule, right? The two hydrogen and the oxygen. And you try to understand how water, for example, interacts with surfaces because you are interested in a desalination membrane, or you want to understand how water interacts with materials because you are interested in artificial photosynthesis. I'll get to that. Many things are actually unknown, even today. And water has been known since 1780. Lord Cavendish discovered basically water. I mean, he didn't really call it water, phlogiston and dephlogisticated air. This is what he came up with. But he did discover water. And the study of water at the molecular scale, as we all know, really impacts science, engineering, but really problems that are of societal impact, like climate, energy, agriculture, and health. And I'll give you some examples in my lecture today. So let me take a couple of minutes to tell you, of course without equation or anything like that, what I mean by computer simulations and what we do in our computer simulation. So this is a real microscope, right, that we are all used to see doing experiment. And basically, to a theoretical and computational person like me, our microscope is a computer in which we actually solve numerically equation that tell us how the atoms and molecules interact. And the equation that we solve, and this is why I want to mention this equation here in San Diego, they are called Kohn-Sham equation. They were basically born here. So these are approximate equation, and they were thought and enunciated in the 60s by two professors who were professors at UC San Diego, and Walter Kohn, who then left, and he's now a professor at UC Santa Barbara. He's over 90 years old. And his younger collaborator, Professor Liew Sham, who is still a professor at the Department of Physics. And they are responsible for the equation that many groups today use not only to study water, but to study materials. You may have maybe heard about the Materials Genome Initiative, pushed by President Obama. This very equation translated into solved numerically are the equation that we solve today to understand many problems. And so Walter Kohn for the equation that they wrote together, not Liew Sham, but life sometimes is not always fair. But Walter Kohn did win the Nobel Prize in chemistry. He's a physicist, but he won the Nobel Prize in chemistry in 1998. And what we do, we solve the equation that they come up and they wrote down and we come up with algorithm and techniques to solve them, and we solve them on very large supercomputers. So we are in Chicago, we are very fortunate, not only because of the University of Chicago and all the interaction that we have in the physical sciences and now in molecular engineering, but also because we benefit from the interaction with Argonne National Lab. And at Argonne, we have amongst the most powerful computers in the world. And we can solve really big problems. We can solve big problems and we can accumulate data that then we compare with experiments, and that we can make a difference. And sometimes, when you are a professor, you spend some time, sometimes a lot of time hearing complaints by students. And, sometimes I tell them, you have to think. You are in a university, in a great university like University of Chicago. Not only that, you have access to Argonne, to the best computers in the world, to the best experimentalists in the world. And, and they still complain, So, this is like kids. And, but really, I think that the combination is absolutely phenomenal. And of course, I'm very, very excited about that. So this is the computational background. And what I would like to do now in the rest of the time is giving you an idea of, by doing our simulation, what are the problems that we solve. And by solve, I need to, it's not that, I'm here to tell you we have solved the problem of harvesting and storing solar energy, or we have solved the problem to control carbon emission. We haven't solved it. But we have made contributions, and I think that the contribution together with experiment actually are quite good. And not only me and my group, but the community working in these problems. And actually, yeah, I know it does work. Okay, so let me start with let me start with the first example of harvesting and storing energy from the sun. So this is the problem of replicating artificially photosynthesis. So you have the sun a lot here, beautiful. And of course, leaves, for you with the sun, do a number of chemical processes that convert sunlight, water, and carbon into material, other chemicals that are useful and then you may want to use, like to breathe, very useful oxygens and other kinds. And you may want to simulate this and to actually make materials to do a natural photosynthesis, not necessarily to breathe, but to produce fuel like hydrogen or to transform CO2 in more benign materials. And just to tell you that this is not only science fiction, this is a device that you cannot yet scale up, okay? But it's a device, wireless, that has just been released by Caltech and by JCAP, which is a joint center for artificial photosynthesis. Our group has been participating in this center and in others that I'll mention, funded by NSF for many years. And this is a device that can indeed split water and do artificial photosynthesis. There are no devices that today you can do. You can take and make and scale up. And for example, bring to the developing world so that they can store sunlight and make solar fuel. But the progress in the last few years has really been immense. And the idea is not new. And many people have been thinking about using so-called radiant energy. And this is a paper, very unbelievable paper scientifically, which says would not be advantageous to make better use of radiant energy. And this was written in 1912. So this is not a new idea. This was presented by International Congress of Applied Chemistry in September 1912. And sometimes when I bring up this paper, my colleagues say, of course, because this guy is Italian, and of course you have to cite your Italian friends. And it's partly true, okay? But this, if you read the paper and you see how incredibly, forward-looking this person is, this is the other reason why I bring up this paper to my student. Because if we really think big and if we think about new ideas, actually we can make a difference. Of course, as we all know, there are a lot of people actually advocating that the better sources of energy are down here, right? And this is very much also a political issue about using fossil fuel, and I will pass. But maybe you can guess where I stand about this issue. So this is a very technical slide in a way, but I choose to present this slide because by all these cartoons here, I want to tell you how many big problems must be solved to be able to actually create a device that can split water, that can do artificial photosynthesis. These are all very big scientific problems, one after the other. And you have to integrate, really, theory, models, computer simulations, and experiment to be able to do that. And we have done this in my group in Chicago together with experimental groups at Caltech, the one that I showed in a center. We have been working on that for almost 7-8 years now. This is a center funded by the National Science Foundation, and we also have active collaboration with the University of Wisconsin. When you look at matter at the molecular scale, as I said that we are doing, actually there are many different problems that look similar. Let me give you an example. If you want to split water, you are not really only splitting water. In your beaker here, you have a solution with some salts. There is some, sulfuric acid is something that you use for technical reason. And this is something that we have studied not only for artificial photosynthesis, but because it's related to the control of changes in precipitations. Let me try to, just in a few words, to explain. So this compound here, sulfuric acid, and combined with water is what you have in your beaker when you want to have a solution to try to do artificial photosynthesis. But it is the same, actually, compound that you have if you are worried and to understand what happens when there are these kind of compounds released in the atmosphere and what happens when there is acidic rain. They produce acidic rain coming down. And the technique that we use, the computer simulation, they can not only do that, but they can also help us understand, for example, how ice in small ice droplet actually nucleate in the atmosphere. And this is important because it's related to the same kind of problems. And this is another program that we have pursued over the years and where we are making progress. And of course, never, this is again something that I always tell my students, never do computer simulation in a vacuum. You need to gather as many data as you can from experiment, validate your simulation, and then make prediction that the experimentalists can verify, which in several cases we have done. Otherwise, don't believe your data. That's because our equations are never exact. They are good, but never exact. Let me get to, of course, a huge problem in the world, and certainly a problem about water scarcity that is present also here, big time in California. And of course, I'm sure that you recognize the picture. This is Carlsbad, and this is a desalination project. I, of course, took this as an example of a desalination project. That's because it's close to San Diego, but many, many people are working in the world to try to desalinate water. From a molecular point of view, you need to find better membranes. Okay, there are many membranes. There are commercial membranes. There are membranes that people are using to desalinate water. But we need much, much more. I mean, I'm always kind of worried about all these numbers when people, and I had several sources for that, and eventually I decided, let me just, roughly say what the different sources say. About 400 million people are using desalinated water, and by 2025, 14% of the global population will be forced to use seawater. So we kind of need to desalinate water in a very efficient way, and especially if we want to do this in developing country. The projects that we have been involved in, again, are projects at the very fundamental level, again, at the molecular level. And we have looked in membranes that possibly could be made of carbon nanotube. What's a carbon nanotube? A carbon nanotube is a foil of graphene rolled up. What's graphene in your pencil? It's made of graphite, of carbon. And if you peel your pencil, you have a foil of so-called graphene, and you roll it up, and you have a carbon nanotube. And this carbon nanotube can have, because of the physical property, can be used, and people are trying to use it as a desalination membrane. Because when you put water into that, and when you look at all the chemical processes that are going on in the water, in the nanotube, you realize that some ions stick, and some ions actually are released. And so you can exploit the principle to maybe use a desalination for new technology for desalination of water. And this is a project that we have had for a long time. Actually, this project, I started this project a long, long time ago when I was working in Livermore at the Lawrence Livermore Lab with many experimentalists there. And it's still going on, funded by other sources, but it's still going on. Carbon nanotube, unfortunately, are not, it's not like I said, you take your pencil, you roll up your, it's not like that. It's much more complicated, and then you have to separate them. And separation technique for carbon nanotube are complicated, and sometimes people use polymers. They use soft matter because these polymers roll better around certain nanotube than certain others. And this is an example where really experiments were made. This is a project that we had in collaboration with Zenan Bao at Stanford. And experiments were made, and without computer simulation, it was basically impossible to interpret them. And our computer simulation interpreted the experiment, new experiments were made, and new ideas were found. So I think that the use of computer simulation to find new ideas is really powerful. Last example is carbon emission. I mean, what does water have to do with carbon emission? One example is the following. There is an initiative in the country. Actually, it's a 10-year initiative funded by the Sloan Foundation. There are very many groups in the country participating in this. We started in 2010, right? So we are halfway through. And the initiative is called Deep Carbon Observatory. And the idea is that we do not know how much carbon is in the Earth. If it's methane, CO2, we don't know. And actually, when we started looking at this, I actually could not believe, I didn't even report statistics here because the error bars are so huge. We don't know anything. And we don't know how much it comes out from the Earth, in which form. And we don't know where the carbon reservoirs are. So, where does water come in? Well, first of all, recently, again, in collaboration with the experimentalists, again in Stanford, we were able to simulate some of the compounds that are deep in the Earth and to understand how the atoms are arranged. But here is the problem. There is water down there all over the place. And basically, you cannot do in situ measurements. You cannot go down there very deep in the Earth and do in situ measurements. And you cannot actually simulate experimentally in the lab very easily. And this is where our simulation came in. And we were able to do large-scale simulation of water under pressure at the condition, temperature and pressure of the Earth, and understand the solubility of carbonates and other systems, and understand what, to some extent, not everything, we never understand everything. I mean, to some extent, understand and contribute to understanding which forms of carbon were out there. And very recently, the simulation were used to reinterpret experiments at low pressure, and we make predictions that were indeed verified about the implication of what we found for water under pressure for reaction in the Earth. And you see here, you see water. These are always our water molecules, always red. And these are diamonds. Why are these diamonds? Because one experiment that you can make to understand water under pressure is to take what they call diamond amyl cells. You have two very powerful diamonds that you use to squeeze your system, in this case water, and to try to reproduce the condition of the Earth. But to some extent, there are some conditions that you cannot reproduce. But anyway, there were some data to which we actually compared our results. The water initiative what I want to say is all the water research that is going on, for example, in my group in Chicago and in several other groups also in chemistry, is now connected to a collaborative water research initiative that has been signed in 2013 between Chicago, Ben-Gurion University, and Argonne National Lab. And this is our president, as you may recognize him, Bob Zimmer, and this is the mayor of Chicago, Shimon Peres. And this is a really important project, not in terms maybe of the size. I think that this project is now funded at the level of $1.5 million, and there are many participants. But in terms of the exchange of expertise, they have a tremendous expertise in desalination, in doing agriculture with salt water in Israel, and that we can take advantage of. We have expertise in experimental and computational science, and I think that this is a very, and so far this initiative has been very successful, and we very much would like to continue that. So before I give you some conclusions of my talk, I want to tell you a few words about the Institute of Molecular Engineering, which is the institute I'm part of, and the institute which was funded at the University of Chicago in 2015. And as you know, until 2015, Chicago never had a engineering school. And the Institute of Molecular Engineering is the first stepping stones for the engineering school at Chicago. And so, of course, people at the University of Chicago who thought about this are smart people. Not me. I mean, people who thought about this are very smart people. I wasn't there yet. And they didn't want to pursue and to reproduce old scientific engineering discipline. And the idea was to have a new approach to academic research and education in engineering, and form people who could master the technique necessary to basically understand matter at the microscopic and molecular scale. And the water example is exactly an example of how you understand these problems at the molecular scale. And the goal was to be organized in big themes and in big topics that would have an influence on society, like energy, water, and information technology, healthcare, and sustainability. And this is a picture that we all use when we try to understand what we are doing with molecular engineering. If you are a scientist, you are basically in this quadrant. Like you do pure basic research, like Bohr, the beginning of the atomistic theory of matter. And if you are in this quadrant, just the old-fashioned engineering, you are more like Edison. And we would like to be like Pasteur. Of course, I mean, it's a little bit too much to say we would like to be like somebody like Pasteur, but please, understand me correctly. Like, to do use-inspired basic research. So this hopefully summarizes a little bit what we are trying to do at the Institute of Molecular Engineering. We have 6 themes: energy, quantum materials engineering, water resources, which I have been telling you a couple of examples about, immunoengineering, and soft functional material and art for science. I couldn't resist. We moved into our new building actually on Friday. I wasn't there, to tell you the truth, but on Monday I will see, hopefully, my office in the new building. This is the new building. It's the Eckhardt Research Center, which also houses the Pritzker nanofabrication facility and several laboratories. And this is my slide to conclude. I only have one additional slide. And I hope I gave you an idea of how we are trying to integrate computation, experiments, and I haven't talked much about this, but data, to be able to study materials and substances like water at the molecular scale. One thing I didn't talk about, because it is not heavily funded in my group right now, but it was in the past, is that Of course, a part of research in water is also related to biochemistry and bioengineering. And for example, this is a simulation that, this is a very sophisticated simulation that we did several years ago about an anti-cancer drug in water to try to understand the mechanism and the reaction rate, and then to speed up the reaction rate so that the drug could be improved. And this is now my last view graph, which is a so-called of publicity for myself, and a new center that actually DOE will announce next week. This is a center funded by the Department of Energy to do computation of computational materials. And by computational materials, I include all the problems that I also talked about here about water. It's called the MICOM, Midwest Integrated Center for Computational Materials. The headquarters are at Argonne, and the participants are University of Chicago, and I've listed those here. We are really very excited about the center. This is the first time that the Department of Energy is funding this center for computational materials. There will be 3 in the country, 1 on the East Coast, 1 in California, and 1 is our center. And with this, thank you very much for your attention. And of course, I would be very happy to take any question about my talk, about Institute for Molecular Engineering, even about Chicago, although probably you all know Chicago very well.
You showed us pictures of some of your faculty members, and currently how many students do you have in the program?
So we have our undergraduate program has just been approved by the university, and we haven't started our undergraduate program, and we will start it in next year. We are welcoming this week our second class of graduate student, and the first class was about 2022, and the second class is about 2022 graduate students. They come from material science, chemical engineering, chemistry, also physical department in the country. And we, at the beginning, were worried, and we still are, of course. We want to attract many graduate students. We had an overwhelming response by students, and the applications were much bigger than we expected. So we were very pleased to see that. Now we have to do well ourselves.
Any other questions?
While we're on this slide here, I'm wondering, when you brought these groups together, is this because these areas of research use similar techniques, or are there also cross-fertilization opportunities between the research of these various groups,
right.
and how does that work?
Yeah, this is an absolutely excellent question. So the group were brought together because a decision was made at the beginning that the focus would be on very big problems and not on engineering, traditional engineering disciplines. And so the problems were identified, and they were identified as energy and energy storage and harvesting, water, information technology, bioengineering, and overall sustainability. Then the people who were brought together here were people who had techniques, for example, that could be used for several of these problems, like our computer simulation technique can be used in several of these problems, and also that were specifically interested in multidisciplinary problem, and that were also especially interested in thinking about new technology really in a different way. Let me give you an example. David Ashalom, who moved to Chicago from the University of California, Santa Barbara, he is a physicist, an applied physicist, interested in hard solid state matter at the origin, and he's studying quantum information for quantum computation and all that. But he is also interested in using coupling his techniques to soft matter for totally different problems. And so the cross-fertilization of having people like him in contact with people coming traditionally from different disciplines, we believe will lead to new ideas and new problems. But basically the idea is, let's identify these problems and let's bring together people who can, in an interdisciplinary way, work together. That's
looking at the list, it looks like, there's a lot of material science, and then there's immunoengineering, which seems to be kind of an outlier. Is that also material science based, or is it?
No, this is not only material science. By the way, there is a lot of material science, but there are a lot of topics and a lot of problems that are being solved in bioengineering, especially by our director and dean, Matt Tyrrell. And all the part of immunoengineering is absolutely not only material science based. There are a lot of different topics there. Unfortunately, I'm not the right person to speak to that. But they have labs with animals that are being set up, and it's not only material science based.
I noticed that most of your funding is coming from government sources. Do you envision or anticipate any private collaboration with the private sector?
Yeah. So we have traditionally, over the years, we have had, I'm talking for myself now, and then I will tell you about other group members. In my groups, we have had collaboration and funding from Intel. And the reason being that, first, all the material science that we have done, certain materials were of interest to Intel, but also because of the algorithm that we developed that were of interest for what they were simulating inside the company that we never got to know, of course, and that's the usual deal. And so we have a collaboration, and we have a small amount of funding from Intel, and then from Shell Corporation. And the Shell is interested in having, for example, simulation of methane and other hydrocarbon on surfaces, and also under pressure, the same type that we would very much like to have additional collaboration with the private sector, especially in the energy arena, in the water. But traditionally, in my group, these were our two sources of funding. There are other groups with Intel funding for other, semiconductor devices at IME, and I may not know of all of them, but there are industrial funding. And certainly, one ideas that we want to pursue is that we want to be connected to industry not only because of funding, but of course because we want our science and technology to be driven by the industrial applications, and for sure.
Other questions? Yes. Sure.
What are the top one or two applications that we might see in the coming years, however long, that would interest those lay people among us? What's going to be exciting coming out of the IME that the industrial applications or whatever that we should be looking for?
So one is, I'm not sure if it's 1 year or two, but so for example, here in the soft material arena, the patterning of new devices that has been proposed by two of our faculty members, Paul Neely and Juan de Pablo, has been added to the new semiconductor technology roadmap. This is actually a very difficult thing to achieve, coming from the academic world. And so devices made out of template of soft matter is something that we will see, and they will come out of IME. There will be devices for quantum information technology and nano-sensing. Nano-sensing in the sense of measuring extremely accurate, for example, temperature and other stuff like that, that will come out certainly, within the next 5 years by David Ashlam group. And there will be codes that are not devices, but are really integral part of understanding these quantum materials, water and whatnot, that hopefully will come out from our center.
Thanks, everyone, for coming. I'm Carolyn Amadon. I am the Director of External Affairs for IME, and I just wanted to follow up a little bit on what Professor Galli was saying about the funding for IME, and we have some wonderful grants that are coming in from the government. But we are also looking to increase our industry partnerships, like Professor Galli was saying, and would welcome any suggestions from people in this room. I know there's a lot of biotech and other folks here about how we can make the connection between industry and funding for IME. And we're also looking for connecting with individual and private donations as well for the work, for the very basic work in all of the labs that you see represented by the faculty and the dean. So sorry for the public service announcement, but I wanted to get that in. Thanks.
Very important for our research.
Any final questions? So my understanding is that both Dr. Galli and Dr. Amadon will be sticking around for a little bit, so please feel free to approach them with any other questions.
All right. Thank you very much.
Thank you very much, Dr. Galli, for that fascinating talk. I was really interested to see the picture of the Carlsbad desalination plant because one of our club members, Bob Pasulka, is actually in the process of arranging a trip for club members, and you can all participate to visit the desalination plant in the next few months. So hopefully now that you've seen this, heard this talk, it will create some more interest in that trip. I'd like to once again thank each of you for coming and sharing some of your Sunday with us. There are many, as Tracy said earlier, there are really many ways that you can engage with the university. You can make a contribution to the campaign. You can take trips with the alumni travel group. You can serve as a volunteer for the Alumni Schools Committee, which is just getting ready to interview the class of 2020, which sounds really kind of spooky. I remember watching Star Trek in the 70s, and Captain Kirk would say, Captain's log, stardate 2025, and I thought, ooh, that's so, far off in the future. But here we are. And of course, you can participate in events like these. And speaking of events, I want to encourage you to join us for the third event in our enormously successful Biotech Speaker Series. So the next event will be Thursday, October 8th, in the offices of Knabe Martin in Carmel Valley. And we have our own Mike Nirenberg, class of 77, and Dr. Yi Liu, who is a parent of a 2019 student. They'll be discussing technology development, finance, and angel investing in the biotech sector. You can register for this event and also find out information about our other events at our website, UChicagoSanDiego.org. And both my contact information as well as Jen Leonard-Benson's information is there, so feel free to reach out to us with questions and suggestions. You can also follow the club on Facebook, LinkedIn, and Twitter. And of course, we'll be sticking around, so please feel free to approach us. Thanks again for coming, and please enjoy the reception. There's still some food and drink. Thank you very much.